So in this video, let's look at Euler equations. So I said in the last video we're going to look at reduction of order, but I completely forgot that our professor did Euler equations before that. It is a little section in our textbook, but it's not really like a whole, there's no examples on it, but there's a few problems on it. They don't give any examples, but our professor went over it. So let's say we have something like this. So an Euler equation would look something like this. Where we have a squared, some squared with a double prime, and if we have something to the first power, we have a to the first power, oh my god, to the first power, and a prime, and an x to the 0th power, and a y to the 1, and just a normal y. You can think of it like that. So this is a Euler equation when it follows this pattern here, where we have these coefficients on top of this. So now for Euler equations, they're kind of like changing everything we've ever known about these second order problems. So what we're gonna do, instead of proposing y equals e to the rt, we're going to propose y is x to the r. And you'll see why this is. Right, so if I do r prime, this would be x to the r minus 1. And y double prime would be x to the, this would be r to the x to the r minus 1. This would be r squared. No, actually, this would be r times r minus 1 times x to the r minus 2, right? So then you plug those in and then solve for our general solution. Now, I think I actually forgot to mention this in the previous videos, but now's a good time to, I guess. But if you have, let me plug these in. So we'll have x squared y double prime plus x prime times r x to the r minus 1 plus, oh, hold on a minute. This is y double prime, which is r times r minus 1, right? Plus x prime times r x r minus 1 plus x to the r is equal to 0. This you can simplify. This will become x to the r times x to the negative 2 plus x prime r x to the r x to the negative 1 plus x to the r. This, these will cancel. Right, I distributed. We still have this in here though. Oh, look at that. These will cancel with this. So then this will just become r squared minus r. Plus, and once you learn the patterns of these, if your professor has you like do a bunch of these for homework or whatever, once you learn the pattern, or on quizzes or whatever, once you learn the pattern, you can kind of just go right to here, all the way up from here. You can kind of just, you'll be able to tell. But anyways, plus, wait, this is an x to the 1, right? So I confused myself there. So then this would be plus if you notice, this and this cancel, plus r plus 1 is equal to 0, right? That comes from this. So this is this, this is that. Now let me just change the color here so you can see that these cancel with that. Okay, anyways, we have r squared, those cancel, plus 1 is equal to 0. This would give us that r is equal to, oh no. Well, anyways, I'm just going to write it like this, but I'm not going to go any further. I just wanted to show what would happen when we get to here. When we propose our general solution, it's now going to be different. Instead of doing we're not going to do this. We're going to propose okay? This is our new general solution. This is only applicable to Euler's equations. Okay? So now let's look at some examples. You can see here, squared, double prime, right? It's an Euler equation. Oops. So first things first, let me get my notes. 27. Okay, so we have t squared y double prime plus 4t y prime plus 2y is equal to 0. Now we're going to propose y is equal to x to the r, so then y prime is equal to rx r minus 1. Y double prime would be r times r minus 1 times x to the r minus 1. That leaves us with t squared, so if we substitute, we have t squared times r squared minus r times x to the r minus 1 plus 4t times r x to the r minus 1 plus 2 times x to the r is equal to 0. We want to cancel out these x to the r's, so that is not a 2. So this will be hold on 1 minute. They give us it with t's, don't they? Just pretend that this whole time all of those x's were t's. Okay. Those were t's the whole time, right? So now, where was I? Yes. Yeah, this is a t. Okay. Okay. Plus 4tr times t to the r times t to the negative 1 plus 2 times t to the r. That's an r. These cancel. This will reduce. 2 minus 1 is that's just going to be t plus 4t times, this will cancel with this. That's just 4r plus 2. Sorry, this is equal to 0. That leaves us with, wait, that t should not be there. Have I made a mistake? Oh, yes, I have made a mistake. When you do the first derivative, I hope someone caught this and was laughing at me the whole time when I did this. When I subtract the 1 from the top, it becomes minus 2. Small mistake, but it does matter. So then these will cancel. Okay. Simplify. This would become, this factors nicely, right? We have r plus 2 times r plus 3. So then r is equal to negative. Oh, wait a minute. No. 1. R is equal to negative 1, and r is equal to negative 2. Doesn't matter what order. Well, I could say R1, R2. So then y, remember, C1, R, so remember it's x. Sorry, in this case, t, they gave us t to the R1 plus C2, t to the R2. So our general solution is C1 t to the negative 1 plus C2 t to the negative 2. Now this is a normal case for this, but there are some weird cases that do happen with these problems, and the next example will demonstrate that. So it's going to appear to be normal, but we are going to have some complex numbers involved. So go ahead, try and solve this one yourself, but you're not going to know how to write the general solution down just yet, because we do have to incorporate Euler's formula, right? From the last video. So let's see. I'll just write it down first. Now we're going to substitute. So y is x to the r, y prime is r x to the r minus 1, and y double prime would be r times r minus 1 times x to the r minus 2. Excuse me. Okay, so now we plug in. This is r squared minus r times. You can almost guarantee that everything is going to cancel. I'm just going to rewrite this like this. You can almost guarantee that everything's going to cancel. You can really just write down this first half. It's pretty much almost guaranteed every single time. But I believe I do remember, it's been a while, but I do remember not every time. It doesn't cancel every time. But I think it'll be pretty obvious when it doesn't. Okay, I'm supposed to plug it in for y prime. Right? So these cancel. I did it again. Those are t's. Those are t's. They have been t's this entire time. You didn't see anything. These cancel. Where's my t to the r? This is supposed to be an r. Jeez. This is how you know I'm tired. Okay. We have... Okay, so this also cancels with this. This should be a t here. This also cancels with this. Okay, and that's it. So we have r squared minus r plus 7r plus 10 is equal to 0. R squared plus 6r plus 10 is equal to 10. So right away, if you can't tell, this is not factorable very nicely. you can either complete the square or do quadratic formula, right? So let's do quadratic formula. R is equal to -6 plus or minus the square root of 6 squared is 36 minus 4 times 10 over 2. That is equal to -3 plus or minus the square root of 36 minus 40 is -4. Right, so then R would be -3 plus or minus 2i over 2, so then that cancels. So plus I. So then R1 is -3 plus I. R2 is equal to -3 minus I. So for this problem, you would have to have watched my last video when we went over complex roots, because this is where we would then use the Euler's equation. But this isn't the normal Euler's equation. Like if you remember from the last video, remember for this one we propose t to the, remember it was e to the first one, remember it was e to the, it would have looked like this if it wasn't an Euler's formula, right? This is what not to do. Don't do this. Don't write this down. Just let me click really quick. So -3 t times, this would be cosine of t plus c2 e to the -3t sine of t, right? If you watched the last video, you would know where this came from. This is not correct in this case. We're going to have a different general solution because we proposed t to the r. I almost said x to the r, t to the r in this case. So we're going to have c1 t to the r, which is -3, which isn't r in this case. It's, right, I said this was a plus bi. So remember in the last video, this was our b and this is our a, right? So in this case, this is our a, and our b, now we're going to write cosine, but it's not going to be a normal cosine. It's going to be cosine of the natural log of b of t, which in this case is 1. B is 1, right? So this is very weird, I know. Plus c2 t to the -3 times sine of the natural log of t. So once again, I'm not too sure where the natural log comes from, but I just know that whenever you have a complex with an Euler's problem, an Euler equation, you write it out like this with the natural logs on the inside. Other than that, everything's the same, except for this e becomes a t instead. Oh, also, there's no t up here, right? You notice that? No t up there. Just t to the -3 and t to the -3. Cosine of ln of, this would be, if you had, say for example, it was -3 plus 2i, this would then be 2t, and this would be 2t. Okay? Okay, I hope you enjoyed this video. In the next video, we're going to look at reduction of order.